notes. Put the X on it. None of it is going to be on the test. Page 2. I guess I would want you to remember that smallpox has been wiped off the face of the earth by vaccination. Page 3, put a big X on page 3. Big X on page 4. Big X on page 5. Is it fun? Big X on page 6. Big X on page 7. Page 8. Let's remember that one of the 3 defenses is the skin and internal mucosal systems. Page 9. Okay, now, start with what's up in 9. Innate versus adaptive immunity. You know this stuff right here. Page 10. I can tell you, but know this. You know, we've talked about this many times, but I want you to, of course, know that B cells start out making surface IgM, and then later they can become a plasma cell that secretes antibody. And just in case I didn't call it to your attention sufficiently, remember that monocytes are precursor cells that can become macrophages. Monocytes become macrophages. Monocytes are precursors to macrophages. I have to break up macrophages into macrophages. And continuing, go page 11A. The most abundant white blood cell are neutrophils. The close tie between them and the lymphocytes, the B and B cell. Lymphocytes come from the common lymphoid progenitor. All these other cells that were on that page that go to the actinome, they all come from the myeloid progenitor. Page 13. The primary lymphoid tissues are the thymus and the bone marrow. Thymus, bone marrow. Primary. The lymphatic fluid comes back into the blood circulation up into the heart, and it's called the thoracic duct. So just a little bit more detail on the thoracic duct. There are actually 2 of them, but we're not going to go into. Page 15. We're going to have to say so much more about this later on. I would say don't worry too much about. I guess you should know that the lymphocytes, which are circulating in the blood, they come into the lymph nodes here in what are called the high endothelial venules. So these are blood veins that have become little capillaries, venules, and that's where the T and B cells leave the blood and come into the immune system tissue, the lymph nodes. Again, not on the test. We'll have much more to say about this on page 15B. Maybe the second test. And don't worry about page 16. We're next on page 16. page 17, we're talking about macrophages here. This is more about the innate immune response here. Macrophages play a big role in the innate immune response. And we have the phagocytosis. They engulf bacteria, they eat them, digest them. Phagocytosis. And then we have special receptors called toll-like receptors. Toll-like receptors. And that initiates a signal transduction pathway that causes cytokines to be released, inflammatory cytokines. Macrophages trigger inflammation. Rubor, calor, rubor, dumor, tolor. Okay. Neutrophils, there's a ton of them in the bone marrow. If you get an infection, they come streaming out into the bloodstream. So if you have an infection, they'll take a little blood smear to see a bunch of neutrophils if we've got infection. Pus is neutrophils. You see infected wound, all that pus, it's neutrophils. Your pimples in the morning that you pop in the mirror, neutrophils. Don't worry about complement. We'll have much more to ask you about complement later on. For the next slide, page 19. Again, as we've been saying, it's right here. This is the structure of an antibody. The arms here, that's the antigen binding domains or the antigen binding fragments. Okay. The T cell receptors evolutionarily related to an FAB, one of the arms or the FAB part. That's basically what T cell receptors. Clonal selection by pathogen. Just broadly, you should know that we make a million different B cells. They each express their own antibody on their surface. One of them might encounter a pathogen. That one will proliferate and have all its clonal descendants who now secrete the antibody. Okay, so we have B cells. Some of them can become plasma cells who then secrete soluble antigen. B cells, one or two of them, they can become a plasma cell that secretes the antibody. We just got finished talking lots about this, but in general, the diversity of immunoglobulin receptors is generated by gene rearrangement at the level of DNA. Page 23. We'll put X on page 23. Page 24. Just remember that antibodies bind the surface of the macromolecule or protein. T cell receptors, they don't bind just the surface of the protein. The protein's got to be chopped up into bits and pieces, and one of those bits and pieces, peptides, can be loaded onto hopefully at least one of the MHC molecules and into a T cell. So T cell receptors see an antigenic peptide presented by an MHC molecule. We went through all this not on the test. You know that there are two kinds of MHC molecules, class 1 and class 2. All cells make and express class 1. All cells. Just a few cells make class 2. These are the so-called professional antigen-presenting cells. And don't worry about them. We'll talk more about them later on. Another name for MHC is HLA. Okay. Class 2 molecules, there's class 2 molecules, they present peptides derived from extracellular antigen. Okay? MHC2 molecules present peptides from extracellular antigen. Okay, that's this. Class MHC1 molecules present peptides from intracellular proteins. Okay? So these are peptides derived from intracellular proteins, yet moving on to class 1 molecules. Okay? In particular, these are viral peptides. So class 1 molecules present viral peptides. Their job is to say, I can't do it, I wish I all my life, I wish I could do that. If they do that kind of whistle, come kill me, baby. Okay, I'm infected. Stop me before I kill again. Okay. There is there's a lot of diversity in the alleles of MHC molecules. Okay? The DNA sequences of my MHC molecules are going to be different from yours. My mother and father's MHC molecules were different from each other, so I have my mother's and my father's. Okay? So for class 1, there's 3 genes, A, B, and C. Each of us has different genes encoding different proteins for the A and the B and the C. So the A, B, and C proteins, these are the MHC molecules. They're broadly the same, but they bind, because the differences in the binding pocket, they bind different peptides, different sets of peptides. So the A gene, C1 molecules, for my mother will bind 10,000 peptides out of the universe of billions of peptides. A different set of peptides are bound by my A gene from my father. So between my mother and my father, my 2 A genes, I can hope to bind a total of maybe 20,000 peptides from very different pathogenic organisms. And same for the B and C genes. So maybe I can bind a total of 20, 40, 60,000 peptides out of the universe of Avogadro's numbers, or whatever, not Avogadro's numbers, but Lagrange numbers of all possible peptide sequences. And why? Populations that have that high diversity of MHC1 genes have survived over evolutionary time. At least some of us will survive if a Mars virus lands here and kills off 99% of us, because 1% of us will have some mutant A gene protein that can present the Mars peptide to our immune system. So not all 100% of human beings will not be killed by the Martian virus. Few will survive, and then will descend from that Adam and Eve pair. So class 1 molecules are made by all cells, okay? And killer T cells recognize the foreign peptides presented by class 1, and they launch hellfire missiles onto the surface of the virus-infected cell. And CD4, so killer T cells, you will remember, are CD8 T cells. Killer T cells are CD8, that's CD8. The other half of T cells are CD4 T cells, and they can become T helper cells. And the T helper cells, they see foreign peptides presented by class 2 molecules. Okay. Page 31, put an X on it. Page 32, put an X on it. page 33, put 33A, put an X on it, and that's it. Page 13. The second handout. So basically, just know that B cells will become plasma cells, and they secrete antibodies. And for a B cell to become a plasma cell, it needs cytokines from T helper 2 cells. Okay? Antibodies contain 2 identical heavy chains, 2 identical light chains. Okay? And you know, these are constant, variable, constant, variable. This is constant, variable for the light chain, constant, variable for the light chain, constant, variable, constant, variable. Okay. And we have hypervariable out here, and that's where we bind the that papain, at just right conditions, will make a single cut and it will release the 2 arms free from the tail. These are the antigen binding fragments, and this is the constant fragment. Or you say this is the tail, the constant fragment, or the crystallizable fragment, as an immersion stood for. It has the constant amino acid sequences found in all IgGs, for example. So these are the fragments, but now you're also referring to the constant, the Fc domain, and the FAB domain. Don't worry about Pepsi. This is page 33E that I referred to towards the end of the first part of our class. Here are the structures of the different classes of antibodies, and here are their functions. You need to know this for the test. Okay? Know this, all of it. And again, we start off making an IgM. IgM, by splicing, the cell can also be producing some IgD, of course, but IgD is kind of a dead end. IgM, by class switching, IgM can become IgG, or IgA, or IgE, by class switching. Now, just remember something that I forgot to emphasize in my lecture. I need to do that. I thought of it here. Let's turn to page. We'll right to this in case, I don't know how I overlooked it, but I just remembered, I somehow overlooked it. Oh, yes. I must have skipped the page somehow. Back on page 45, we were talking about how membrane-bound IgM can, by altered splicing, become secreted IgM. That was page 45. Now somehow I skipped, very important, page 46. This will be on the test. And pull up the color version of it. joint department on this. Remember I said, here's the DNA, and we're a B cell. We finally made a B domain here, BDJ. We assembled all this, and now we can start making mRNA off of this, or primary RNA transfer, which is going to contain C mu and CD constant sequences, which we use splicing. But then we have all the coding parts for the other tails that can make you an IgG or an IgD or an IgE. And so in the lymph node, after we did hypersomatic hypermutation, and the kids are on the ice cream cone dealer fighting with each other in the highest affinity one. After we select the mutated B cell with the highest affinity, we then do class switching. And in class switching, we will then here, let's say we can class switch between an IgM, so we're going to loop out here, this C mu and CD are going to loop out, and we're going to bring in the C gamma 3 right next to the BDJ part here. Okay. So now we splice out the IgM and IgD sequences and throw them away as a circle and so forth. And now we have the BDJ parts here, the specificity, and right downstream from that is the gene for a constant domain for inhibited globulin G, C gamma for inhibited globulin G. Now there are several different kinds of IgG, and this is the IgG3. Don't worry about that. So now we start making and secreting no longer IgM, but IgG, actually IgG3. Okay. Now later on, we could then, so we looped out, threw away U and D. We can never go back to making IgM or IgD because they've been cut out and thrown away. But we can't go forward downstream here. We could later on switch from making this next to the BDJ. We could move further out and pick one of these to be next to the BDJ. So here we're showing how we could then go from this being joined next to the BDJ to, let's say, an IgA constant domain, C alpha, and there are two of those, okay? So here we could loop out again. Here's the IgG, and then C gamma 1, gamma 3 gone, and now we're bringing the IgA box, and now we're going to be having our variable angioline domain hooked to the tail of an IgA protein. Is that clear? But you could never go back to IgG3 or whatever. That's gone now. So you can do some class switching down the road, sequentially, but you could never go back. You can never go to the left here, and that's all been cut out and thrown away. And there'll be a question on the test asking you to grasp the idea that there's a kind of a directionality to the class switching. Once you've got to some class switched, the intervening ones are gone. They're no longer an option for you because they've been thrown away. But only maybe 30 downstream to the right is class switched.
So I have a question on that.
Say again?
I have a question.
Yes.
So does it happen after the base of us?
That happens in the lymph node after somatic hypermutation and fine driving to the highest source,
So we
the
have,
highest
we have
affinity.
several plasma cells in our, do we have only one plasma cell that has that many affinity or multiple? I'm
Kind
wondering,
of muffled, but say it again.
I'm wondering basically, are there multiple different types of plasma cells that can make IgG?
No,
IgG?
for a given infection, there'll be some lymph nodes involved. There's the site of infection. And depending on what the pathogen is, some fraction of those cells may become ultimately IgG, but maybe some of them will become IgA as well. And then later on, you'll be making even more IgA, or maybe even switch to IgE. But it's not uniform. You could have some of the cells that were originally IgM, they can later on become, their clonal descendants can become mostly IgA, but maybe also some of them are now IgE.
Okay, that's what I was asking.
Yeah, does that answer?
Yes.
I'm glad I realized I had told you that, because one of the questions. Okay, so note this on page 46. Don't worry about page 47. This will be on a later exam. Take X on page 47. Don't worry about the details here on somatic hypermutation. Just know that somatic hypermutation occurs, and it's focused on the hypervariable parts of the gene that codes the hypervariable parts of the protein. And this is just a summary. This again, I told you need to know the main functions of the main different kinds of antibodies. Don't worry about all these details up here. Put an X on this table. Again, you just know the main antibodies. Put an X on the table. Don't sweat the table over here. Don't sweat the table. For the 20th time, 10 antigen binding sites. Anybody misses that question? That must not have been here. IgAs, dimers. 54A not on the test. 54B you don't even have it, but it's not on the test. And then graduate students. And we will finish. Start on this. After 45 minutes. 33E.
And then you went to.
33, 47. Yeah. Well, sorry, kids, we'll take another minute or two here, just to make sure. Oh, yeah. Monoclonal antibodies. Now, I told you, actually, I was emphasizing this in my lecture already. Okay. Keep that. I've done quite a bit of it. So, anyway, so no affinity versus avidity on page 34. Affinity versus avidity. And know that if IgM would have, what would happen with IgM, would that be better for affinity or avidity? Right, avidity. IgM, avidity. Overall persistence of the whole antibody protein being bound to the surface of one of the 4 arms is always going to be bound. That's the avidity. Okay, don't worry about 34. Don't worry about 35. Okay, monoclonal antibodies is going to be on the test. Really, I already told you everything I want you to know about the monoclonal antibody stuff. Okay, always remembering that the myeloma cells, before you even start using them for the fusion process, have been selected to have 2 properties that they did not originally have. Property 1 is you select for ones that are mutated and lost the ability to make whatever endogenous antibody they were making before. That's gone. Now the only antibody they can make is that will come from their B cell partner. So you get rid of the endogenous antibody gene that they have, get rid of that. And the other thing is you select them to be HGPRT minus. So that they cannot grow in captivity. Okay, then 37 is, I'm not going to make you go all this time, so don't worry about that. You get the main idea of all these things right here. You just select them and cut them. There'll be a test on page 39, as I said. You're going to be on the test. You're going to give you some numbers and you're going to tell me what's the diversity that you got to remember that the constant domains do not contribute to the antigen. Not on the test. Not on the test. Except know that you add N and P nucleotides to completely give the diversity numbers become astronomical because of inhibition of these nucleotides here. Truly astronomical. 10 to the 14 diversity you get out of this. 10 to the 14. Yeah, billion would be 10 to the 12. So, it's 100 billion. Don't worry about this. If you don't have this, I'll either remember to make a photocopy or there's a handout here, the useful page. Be a onto medical school immunology course. And I'll try hard to remember to post this on our course. Okay, remember alternate splicing between IgM and IgD. Don't worry about the enhancement of promoter stuff on page 43, the link X on page 43. It's just a summary figure. And then also, switching from making a membrane non-protein, here's the membrane here, to making an integral membrane antibody versus a secreted antibody, that's again alternate splicing of the RNA. This is RNA alternate splicing. And then isotype switching. Don't worry about page 47. Don't worry about the details on page 48. Summary, and I think we already talked about this. So we're done.